And welcome to another week of AI Saturdays. Don't know whether this is only AI Saturdays Lagos anymore. It's AI Saturdays Global now. So when you're big, you're big. So morning again. My name is Tayo, and this week we'll be looking at relational data and how it applies to data science. Yep. So let's get started. So the outline for today is going to be, we're first going to look at relational data, understand what relational data is, then we'll understand what entity relationships are, then how to carry out relational data operations with respect to data science using pandas and SQLite. And then we're going to look at one very, very important topic when it comes to data in any form, joins. Okay. So starting with overview of relational data. So before we get into it, please, if you have any questions, don't hesitate to raise your hands or drop your questions in the chat. Should we do what we did last week, the class captain volunteer?
Yes, please. Who would like to be this week's volunteer? You can raise your hand or unmute to speak. No one wants to be class captain.
Okay, that's fine. I guess I'll just pay attention to the chats or look.
Don't worry, I'll be your class captain. I'll be here. I'll monitor. Oh, Tayo, you wanted? Don't be shy. You wanted to volunteer?
Okay.
All right, thank you.
All right, thanks, Temitayo. All right, let's get started. Okay. So now it says, what is a relation, right? So what's a relation with respect to data? Relational data or RDBMSs, that's relational database management systems, they typically involve using tables. So tables are the bedrock of relational data. And so when you have data in a table that is structured, then you can say that you have a relational data. And let's go away from the technical and let's look at the literal meaning of relation and help us understand why they decided to use that name for data or with respect to data. So when you say relation, you actually mean that there's something that brings one entity and another one together. So that's if we're looking at two different entities, but within an entity, there are also some attributes that you can say belong to one entity that are also related. So all those attributes together, they make up a relationship within that one entity. So I have mentioned two things now. I've said entity and I've said table. So now if you look at this example here, we have a table. This table, depending on the name that it is given, so they say an instance of a person relation. So relation can be interchanged with table with respect to relational data. So when you say a relation or a table, we are typically referring to the same thing, right? So if you give an example of this person relation, now this relation, this person could also be known as an entity when you're talking about relational data. Person is also known as an entity. And each of these fields, they are called fields or columns. So column ID, column last name, column first name, column role, or features ID, last name, first name, and role. They are all attributes of the person relation, of the person entity. Are you getting me? And each of these fields are related to this entity. because they are attributes that belong to this entity. So do you understand now? So that's the whole idea of the naming convention, relations, and table. So you have ID, which is one feature, the last name, the first name, and the role. So in other words, you can say, given this relation, a person is made up of his ID, their last name, their first name, and their roles with respect to what we're looking at. Is that clear?
Yes, sir.
All right, thank you. So now, whenever you have tables, each row is a separate observation, right? Each row in a table is a separate observation, and it is known as a record. It is called a record because records are meant to be unique to each row. In other words, what it's telling us is that row one ideally should never be the same as row two and shouldn't be the same as row three or row four or five in one table. Whenever you have that, you're introducing some level of redundancy, but that is not the way a table should work ideally. Each record needs to be separate from the other one, even if it is just by a single field. It has to be unique. So, and each row is called a tuple. Each row in a table is called a tuple. And okay, so that's what I say here. It's called a tuple or record, like I've mentioned, and it represents a single instance of the relation. So like I said as well, it must be unique, because if it is not unique, you're defeating the purpose of having a table. You need to be able to say row one is different from row three and different from row five. It should have a unique identification. It should be a separate record on its own. I don't know if that is making sense, but it is very, very important. We need to emphasize that. So, like I had mentioned earlier, each of these fields or columns are known as attributes of the relation. So the ID is one attribute, the last name is another attribute, first name is another attribute, as well as their role. It is an attribute for each of the records that we have. Okay, thanks, Temitayo. So we have looked at a single table. Now, when you have multiple tables, what is the relationship between them? Like, what that means is we have looked at what one table looks like. We've identified what a row means, what a column means, and the fact that each row needs to be unique. But the beauty of relational data is you're not just looking at it in relation to itself, you're looking at an entity in relation to other entities. So that's why you need to have relationship between tables or entities. So now look at this interesting scenario. You have a person table and you have a role table. Now, what is the relationship between them? As you can see, the person has a unique ID, which is ID, has their last name, also has their first name, and then the person has a role ID. If you go to the role table, the role itself has an ID and it has a name. What that is telling you is the relationship between the person and the role table is this role ID. This role ID, which you can get from the role table. In other words, what that means is Zico Coulter with role ID 1 is an instructor. That is how you read these relationships. Josh Williams with role ID 2 is a TA, a teaching assistant. And William Gates, who is role ID 3, is a student. You can also see that each person here can have, each person has a unique role, but this role can fall to multiple people. We're going to get back to that further ahead, further down the line. But this is how you explain relationships between entities. Now, what role ID is doing here, what it is serving us, we're going to look at that in the coming slides. So I just asked, what does role ID stand for? But first and foremost, what does ID in this table mean, and what does ID in this other table stand for. Now, IDs are typically identifiers, and for them to be able to do their jobs very well, they need to be unique identifiers. That's the way to separate record 1 or record with ID 1 from record with ID 3 and so forth. They need to be unique. So the person table has a unique ID column or a unique ID feature, while the row table also has a unique ID feature. And that is why you can see role ID 1 here and know that it belongs to instructor. And any other place you find the person relation and they say the person with unique ID 4, you can always come back to the person table and understand that that person is Mayank Jane. Does that make sense?
Yes, sir.
Hey, please just say yes. Just say yes. Thank you. Okay, so let's go on. Now, what these IDs, like we have said, they are unique. Okay, Elizabeth. I'm going to go
Want you
over
to
it.
go over it again.
Yeah, I saw that. So now we're looking at primary keys, right? We have said that this ID is a unique identifier. And what a primary key is any attributes, any feature of a relation that helps us identify each record uniquely. That's what the primary key is. The primary key is a unique feature that you can use to identify each separate record in a relation. So in other words, the ID column here is the primary key. You can see that they are all different. You know, in this table, you could have two different people bearing Zico Coulter, right? But their last names will be Zico and their first name will be Coulter. Their last name will be Coulter and their first name will be Zico. But what separates them is going to be their ID. That's the way you know that that's a separate person, and that's the beauty of the primary key. That is its primary function. Exactly, Babalola. Exactly. So, and the same goes for the row table. The primary key is the ID 1, 2, 3, such that whenever you want to make a reference or map, like Babalola mentioned, or map something within this row table, you only need to call on its ID, on its primary key. So now what is the primary key of one table, of one relation, doing in another table? It's in the next slide. At that point, it has left its home to become a foreigner somewhere else. And that is why it is called a foreign key. So a foreign key is simply an attribute that helps you link a particular relation to another. It helps you identify what that relation or what that record means in another table. So it is helping us know that Zico Coulter, who has the role ID 1, is actually an instructor per the role table. Does this make sense to you, Elizabeth? All right, thank you very
Yes, you
much.
said yes.
Yes, I've seen that. And others too, please feel free. You can type in the chat and let me know where I need to go back. But I think this concept is very simple enough. You want to know what the person's role is. Instead of writing the name, the best practice is to use the role ID. So now, if you say, can the foreign key be null? Unless null in itself is an entity and not null as in nothing, unless null is the ID in the table that it belongs to, then you shouldn't be having a null foreign key. Or better yet, another case would be that if someone doesn't have a role ID, if the person doesn't have a role per se, then there's a possibility that this role ID column could be null. What that simply means is the person doesn't have a role yet. But then, like I said, in database design and best practices, those scenarios would be represented in the best way. There has to be a convention that is followed. Does that make sense, Theodora? All right, good. And another implication of, or something related to the question that you asked is this line. If you delete a primary key, then you need to delete all foreign keys pointing to it. So what that means is if you delete this record student, right, then you know that William Gates and Elon Musk have to be deleted. Not their records, their role ID has to be changed to null because they are no longer pointing to an existing key 3. If you remove 3 from here, then you're going to have to delete these and change them to null or change them to the convention that represents that they don't have any role in the system. Is that clear? So, all right, thank you. So the next thing that we're looking at is indexes. There is a typical problem, a very popular problem in computer science, and it is searching. And what that has to do is with your space and time complexity. I don't want to geek too much about it, but it's a core computer science concept, your big O notation, right? That is what this guy is, big O. And what it checks is your space and time complexity. Now, why that is important is because your computer, whenever it has anything to do with records, a fundamental algorithm that your computer runs is a search. And when we're talking about computational expenses, we are looking at space, which is memory, because it is a premium when you're looking at your computer. Space is memory. And you're also looking at time. What that means is you don't want to take up too much memory when searching, and you also do not want to waste time. I mean, if you click on something and it is taking forever to load, that is already bad user experience. So for every operation you want to carry out on your system, you are looking to optimize your space and time, right? So that's how I can explain, or that's the prerequisite I can give you for what I'm about to explain. So when you have, or when you're talking about indexes with respect to databases, you are looking at ways to quickly access the elements of a table. So now they say, consider finding people with the last name Gates. Does Adura have a question? Or he unmuted himself by mistake? All right, thank you. So if you wanted to look for someone in this table without an index, what would that tell you? It means you're going to have to look through everywhere. You're going to have to check the first person. Are you Gates? No. You look at the second person. Are you Gates? Number 3, are you Gates? No. Then you get to number 5. That's if you're lucky that Gates is not the last person. You get to number 5 before you find Gates. What that means is you are going through all the records. And in algorithm terms or space-time complexity terms, that is a big O order of n operation. It means that you're going through all the records at least to find what you're looking for. Do you understand me? That's very simple. It means you're going to go through all the records before you find a Gates from there. So introducing the index, right? So now they say, think of an index as a separate sorted table containing the index column and the tuple location, such that searching, yes, thank you very much, Teju. I didn't have that. So remember I said, if you're lucky and Gates is not the last record, so that is a worst case scenario. Exactly. So when you're talking algorithms and time, space, complexity, big O notation, you're looking at the worst case scenario. So the big O notation would typically represent your worst case scenario. The worst case would be that if you're looking for someone or you're looking for something, you're going to go through all of the records contained in that table. So, but what an index is going to do is typically have your records sorted and contain a pointer. Do you understand? It is going to have your records sorted and contain a pointer. So what that pointer is going to be is going to point to the location of your index column and where the tuple itself is. The tuple, remember, is each record. Each record in the table, that's a tuple, is a separate tuple. So it is going to point to it, and automatically your search time or the complexity or your big O in the worst case becomes the order of log n. For any n, the log of n is typically very, very small. So, and the larger your n is, okay, so I don't know that relationship. I don't know, let me say what's wrong. But typically, whenever you have order of log n, this is a very, very good time. This is a very, very good big O. So in other words, what that means is your database or the way databases are designed, having known that you can do this, they employ the best data structures. They try to employ the very best data structures that would enable databases search for records in the best possible times. And that's why they use data structures like B trees. Now, I don't want to get into what data structures are, but data structures are simply structures. They are ways that your computer store information, how they store things in memory. So when you use a binary tree or a B tree, like he has called it here, you realize that searching, looking for items on your table becomes a lot easier because of the way the data structure works. Does this make any sense? Should I go over it again, or we're clear to move to the next scene? Okay, I'll move on. So basically, okay, just one. Now hear me out. What the index is going to do is have your table sorted, so to speak. It's going to have your table sorted in a way. Tejo has a question for the class. Does anyone know what a B tree is? A binary tree? Oh dear.
Thanks, Theodore. So would you like to explain to us how you understand binary tree? Just a rough explanation. I just wanted to get a conversation going to see how someone else in the audience can explain to their colleague how this sort of tree searching works. Not to go too in depth because that's not the purpose of this class, but it's good to have some conversation going in class.
Okay, I don't have to unmute my video for this, right?
That's okay, you don't have to.
Okay, what I understand by binary tree is I can't quite, it's just like a tree with a root and children coming out of it. Like for example, let's take a root node as let's say school, then the children under it could be like faculties like computer science, blah, 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 that connect to that root node. That's how I quite understand it. I'm not really sure if that's correct, but
Yeah,
that's what I said.
yeah, thank you. That's a good enough intuition for us to work with. Now we already know that binary tree has something like a root. It has children, and because it's binary, it seems like it has to always split into two, right? You know, for the name of binary. And if you can look at the link shared here by Taya, we can already see that it looks somewhat like that. Osage, would you like to to share how you understand B-tree algorithm.
Okay, can you hear me?
Yes, I can.
Okay, good morning, everybody. Yeah. Well, basically, binary tree is just like let me just say it's a non-linear data structure. Normally, we understand that data structures are usually like arrays, sets, and all. They're usually in that linear format. But binary trees follow this non-linear structures, which makes them, as the tutor said, very useful for searching, because instead of going through the whole structure, it goes through each specific node and does the search uniquely, making it very fast. That's just
Thank you. Yes, I think that's enough idea just to help us see. I just wanted to ignite our curiosity. That would also help us maybe Google search the term, see what it is. Is is it important enough for you to understand? Because these are really important concepts for you to understand. So, but there's no way we could go over all of that in this cohort. We can only try to ignite your curiosity. Someone asked, is it like decision tree? And I found a post which might be useful. I mean, decision tree also uses this tree structure, and might be interesting for you to have a look. Is it the same reasoning between B-tree and random tree? Yeah, sort of like the algorithms, like the idea is very, very similar if it's not the same. So you can also have a look at the link.
Yes. And to answer Alfred, no, it is not like the Pascal's triangle. It's not. Is it like a decision tree? Like Teju said, very similar, because you have nodes and branches, right, on any kind of tree, and they kind of work in the same way. You have to make a decision at that point. But while the decision tree is making a decision per se, in your binary trees or your search trees, you're actually asking a question. You're looking for something. So the decision you're making at that node is it greater than this or is it less than this?
Like, is what is the variable I'm looking for? Is it here? Is it greater than? If it's not, then let's split to another thing. Let's look at that. If it's not, then we split.
And why that is very good is for you asking that question at that point helps you know that you don't have to go to the other place if the answer is no.
Yeah.
So it has reduced your search time at that point by half. So if you continue to toe down that line, you realize that a lot of unnecessary movements has been shelved off the way because of the decisions that you're making at different nodes. So that's why it is very good for searching. Do you understand?
And you can
Does it look like more like a while true loop?
Yeah, so while true for this, or if something, as long as it's a condition, whatever you're doing at that node, at that point, is a condition. So while, if, they are conditional statements. So depending on what you're trying to implement, so because the trees are not only implemented in terms of numbers or anything, as long as you have a system that has some form of search or hashing in there, you can implement it. You have to implement that node with a conditional statement. So whether it's a while, whether it's an if or thereabouts. Does that make sense?
Yeah. And you can already see why it's important for you to sort this before you run the algorithm, right? Because like Tara said, you're trying to split. I like to think of it as how Professor Bloom, I said Professor Blum, David Marland from the CS50 course, would say that if you're trying to search, like you have a phone book and you want to search each name, so you can either go one by one until you get there, which will take you like N, like other big O of N, right? Or you could do it a lot smarter. You try, knowing that the phone books are sorted, you can just try to start, maybe you start in the middle and then you look at where are you in J? Is the name I'm looking for, like maybe it's B, okay, then you know that it cannot be in the right part of it. You tear the book open, you throw it away, then you go again, you split it open. Am I, where am I? Oh, you know it cannot be in this, oh, but then you say it, you throw it out. You know, you should watch the video for CS50, Introduction to Computer Science. It's always very funny the way he explains these concepts, and you know, it's kind of like give you the intuition that you need for how this algorithm, such an algorithm might be behaving.
Yeah, thanks a lot for that, Teju.
No worries.
That sounds very visual, and it's one of the best ways to learn, really, when you see things happen visually. So, with this said, everyone, I think we have a very beautiful idea of what the indexes stand for. They are simply saving us the hassle of having to go through everything, and they stand as very good pointers to be able to search on time so that your wait time is considerably reduced. It is optimal. Yeah, so think of it as primary keys has always been a fast way to access data, and they don't have to be on a single column. You can have an index over multiple columns. I'm not going to say too much about that, but typically whenever you have, given that your primary key or your primary key always has an index associated with it, I can go out of my way to say, in the cases where you have more than one primary key, it is called a composite key because it's consisting of more than one key, but that's by the way. Just trying to tell you that where you have an index over multiple columns, there's a name for it. Okay, so the next thing that we're looking at now is entity relationships. We have successfully looked at what one table entails, how it is dealing with itself, what everything stands for, and how it is able to help you easily churn out results from querying it. So let's look at what entity relationships are. So quick question, how many of us have computer science backgrounds here? And how many of us are familiar with the term ER diagrams? Okay, sweet. So you can see that, yeah, very good. I like the responses I'm getting. So you'd understand that these four are not alien and they literally mean the same thing. But let's go over them again. So you have your one-to-one relationships. You have your 1-to-0 or 1-to-1, depending on the notation you use. You have one-to-many and many-to-one. Then you have your many-to-many. The meanings are in the name. Literally, it's one of the beauties of computer science. Things are named in the simplest possible way. Nobody's out to get you in computer science. Like, they name things in the simplest way so that you can understand what it means. So note that these relationships are really between the entities that the tables represent. You understand? Really, like the relationship is between the entities. So look at the entity beyond just the table that you are seeing. What that means is if you have a person table, the person table might have an ID, first name, last name, and row, but it doesn't mean that those are the only attributes that person entity has or represents. Do you understand? So you are looking beyond just the table. So the relationship is between the entity in itself, the entity in itself being a person at that point in time. But like I said, we won't go beyond that. Just so that you understand that you look at things beyond what is in the computer, look at it as a literal item, as a proper object. So the one-to-many relationship, what this means is a one-to-many relationship means one entity, right? One entity could have many relationships. One entity or many people in one other entity can have just one of this entity. So think of it like this. Many people, person, so when you have many, this bird claw notation is used to represent many. And when you have row, so you could either have a vertical line just across it or like this. What this means is just one person, many. So what that is saying is many people can have one role. That's what this notation means. Many people can have one role, or one role can apply to many people. That's the way to explain the one-to-many relationship diagrammatically. So one role can be shared by many people. That's it. And we can see here, row one is only one person has row one, but it doesn't mean Williams cannot be an instructor as well. As we can see that 3 people have the same row, TA. So this one row shared by many people, Williams, Dan, and Jane. Do you understand? And the student role is shared by many people, Gates and William. Sorry, Gates and Musk. Does that make sense? I think it's very simple. So the one-to-one relationships. So now what one-to-one relationships represent is each element in one entity can only match to one other element in the other entity. You can't match to more than one. It is one-to-one. Whenever you start having one-to-many or one record matching with another person, then you no longer have a one-to-one relationship. And there are very, very peculiar cases where that has to hold. For instance, in this example now, the person and Andrew ID. So yeah, that's my unconscious bias there. So the Andrew ID is a unique identifier for students at Carnegie Mellon University, right? So it's a unique student identifier. What that means is no two people, whether student, faculty, or staff, no two people should have the same Andrew ID. So now if you have a separate entity called the person, right, and an Andrew ID entity, then you know that each person must have a separate Andrew ID. It has to be one-to-one. Otherwise, there's going to be a problem in the system. The system is going to break. So the example here is one person has just one Andrew ID. It's as simple as that. A person, Zico Coulter, with role ID 1, has his own Andrew ID, Z Coulter. And how do you know that it belongs to him? His ID is the foreign key in the Andrew ID table. So that's how you know that it's for Zico Coulter. His person ID is 1, same as Williams Josh. His person ID, which is 2, is the same here, and that is what his Andrew ID is. No other person is going to have this Andrew ID, and so on and so forth. Does that make sense? That is a one-to-one relationship. Very, very, very important. So 1-to-0 or one-to-one relationships. Now, what does this mean? What this means is when you have two entities, you could have someone in one entity could have no representation in the other entity or one representation. So it's 0 or 1 representation, and I'll explain. So the premise for this example is a person and their homework grades. And what I is saying is you could have a person without grades for the homeworks at all, or that person is only going to have 1 grade for each homework. Do you understand? So as you can see, for this person, he has a grade in homework 1, also has a grade in homework 2. Now there's a possibility that there's another person who has 0 or null per se, meaning that the person doesn't have any grade for homework 1, neither does he have for homework 2. But we're going to look at that in the next slide, or at some point over the course of the class. We're going to explain that. So many-to-many relationships. Now this is very interesting. So what that is telling you is that many instances of one entity could represent many instances in the other entity. So as you can see, you could have many homeworks for person homeworks. In other words, what that means is the table that represents each person and the homework they have done would definitely have more than one homeworks, would definitely point to more than one homework in the homework tables. Now let's look at this example. Sorry. Let's look at this example very well. You have an homework table that is simply the homework ID, the name of the homework, and the points for the homework. So homework 1 is homework 1, homework 2 is homework 2. And you can see here that this person with person ID 5 has done homework 1 and has also done homework 2. So what that means, and you can also see that person 6 has done homework 1 and also done homework 2, meaning that this same homework 1 has been done by 2 people. Homework 2 itself has been done by 2 people. It also means that this person has done homework 1 and 2, and this same person has done homeworks 1 and 2, meaning many here, many here. Does that make sense, or should I go over it again? Please ask the question. All right, thanks.
Makes sense for now, at least. Maybe when we see practical.
I just have a quick question for everyone.
Yep.
Why do you think we need to understand relation? Why is it important? Why are we going through all of this? I find it that it helps whenever you think about why you need to do something. It kind of like just help you focus a little bit more. So I'm throwing it to the class. Does anyone want to tell us?
Okay, I'm raising my hand. I was hoping I would be called.
Oh, Akintayo, I'm sorry. Thank you. You're cold.
Yes. Okay, so far we've been familiar with handling files and tables and rows from our files, and there are kind of different kind of data that you might be dealing with. But the place of relationship is when you're working with more than one table or more than one, should I say, structure, data set. Let me use it that way. So you might need to find a way that a data set is interacting with another data set. And I suppose that was why they thought was about foreign ID and the primary ID. That's a way to bring this relationship. And then that's why we call this a relational database, I suppose, my own belief.
Thank you, Tunde. That makes total sense. So as a data scientist, why would you need to work with multiple tables? Is that like a given? Do you think you would have to work with multiple data?
Not all the time, but progressively data are being collected from time to time, and we might have a little bit of updates in our our database. So we might have the updates coming in as new rows and columns, and then we can have the updates coming in as an entirely new table. So in situations like that, when we are gathering data sets, even as data collectors. We are trying to ensure that the data we are bringing in are fresh, is relating with the one in the database, and then so that when analysis are being done, we can actually bring a relation and correlation between them.
Super. That's
Yeah.
a very, very brilliant answer. Thank you so much for the interactive conversation. So on the chart here, we have also answers. So data, you said, because we are going to be dealing with data manipulation, yes. And for proper tracking, Adara, what do you mean by proper tracking? Do you want to speak? Okay, Tawak said to understand databases, that's also part of the goal. And Adedayo said, so we have to understand the relationship between different data formats. That's also a part of the goal. So during data collection, you may need to work with multiple tables. Yes, you're right. That's also part of the goal. So I think in general, we all have a good understanding as to why, as a data scientist, it's important for you to understand how to relate different multiple data sources, like understand what it means to work with a database or table, or like to join data and whatnot. So I think it's good. It's enough to wake you up if you were already sleeping in the class.
Yeah.
I'm sorry,
Yes,
and for network. I'm really sorry.
Sorry about your networks, but again, thank you for the conversation, and thank you for the understanding of shown. Understand why this is important, because like Teju said, you are going to be working with data from different sources most of the time, majority of the time, and a good scenario is when you're trying to do something and you know that you're supposed to work with a particular entity, but if information about that entity or that person or that thing that you're trying to do your data science operations on, if the information is contained in many different places, you have to find a way to aggregate everything. And this is one very, very interesting or powerful tool concept that you need to have in your arsenal to be able to carry that out. So again, thanks for your contribution, and hopefully it starts to make a lot more sense. You can start to see it a lot more practically. Okay, so associative tables. What is an associative table? Can looking at this this example, this personal mock table, what can you call, or what would you define an associative table as? Anyone from the audience can go ahead and raise your hand. Anyone?
Okay, in my own little understanding, it is
Yeah.
that table that is kind of bringing more than one table together to relate with a different, to a particular feature.
Thank you
I
very
think,
much.
okay.
Does anyone
Associative, yeah. So
Okay.
associative tables are tables where two or more are situations where two or more tables are related by their ID. So for example, you can have a users table. So the users table maybe contains so a user here can be like footballers, a table for footballers. So that would be, it just contains all the information about footballers. Then you have another table for clubs, right? So you now want to link the two by their ID. So in the footballers table, you can have, a footballer can have a club. So to link the two, instead of putting the name of the club in the footballers table, then you can now put the ID, so that you can link the footballers table to their clubs table. So that instead of having duplicated data, you just have the ID linking the footballer to the other table. So that's an example. So associated tables are pretty much tables where we are linking two or more tables together using ID or associative columns.
Yeah, thank you very much, Mustafa. Enichukwu, you raised your hands. Can you go? I'm seeing interesting answers in the chat, and I'm going to get to them.
Yes, I did. So from my own understanding, I would just call an associative table more like a fact table that contains
More like a what?
whole,
Sorry.
a fact table. That's a fact table where you have dimension tables or fact tables, right?
Sorry,
So
spell facts. Like, I can't hear you. Do you mean FACT?
Hello?
Did you mean FACTS?
Yes, I mean
yeah, a fact table. Can you hear me now?
Yeah, I can hear you.
Yeah, that contains the whole information, more like it has that contains major informations from different tables. Okay, like for this one, we could have for this one now, for this person homework, we could have a dimension tables where person IDs could be a primary key in the dimension table, which could have other columns where the person's name and then maybe the person's class could be in, right? And then we could also have another dimension table, which homework ID could be a primary column, a primary key, sorry, there. And then it could now have the different homeworks as the column names somewhere, right? So this table now links to those two different person ID and homework table, rather person table and homework table. So that's why I said it's more like a fact table, which takes information from different two-dimension tables or different dimension tables, rather.
Yep, you are very, very correct. Very, very correct. And I'm loving this conversation. Joshua says associative table is the middleman table. And that is just a perfect term. It's the middleman table, the link between two tables. Just, you didn't tell us how they're linked, but yes, that is what it does. It is a middleman table. Theodora says it links two tables based on their primary key. You could literally just join Joshua and Theodora's answers to get the full definition. It's a middleman table that links two tables based on their primary keys. And what is it keeping exactly? Facts, like Chizoba said. So it is a facts table. Now, why associative? Temitayo, you have a question?
Yes, the question.
Okay.
Okay, so in real life, because if we're just dealing associative tables, there are situations when working with databases that you have maybe when writing your queries, you're linking a particular table with two or three other tables, but the table itself contains enough data, like enough information. Say, for example, now we're looking at a table of people in this class, and then in this class, there are people that do Python, there are people that do JavaScript. There are some persons that do HTML and CSS, but they don't do JavaScript. Now, there are times that each of those tables are actually going to relate, and there are times that each of those tables actually, there might be tables that contain information of two or three persons. For example, people that are in HTML can have ID of people in Python, because you can actually get to HTML using Python, and also JavaScript people. In that situation, HTML table, is it serving as solely an associative table, or is there any other thing that we can call it?
Okay, so I get what you're talking about, and that's a very, very peculiar case. It's similar to this. So think of it like this. You have, let's try to name them, try to maintain convention. So you have the participants table, that's each person. You have your name, your unique personal ID. Let's say it's your email address in this case. So Temitayo something, Tayo Jabar, Tejo Afonja, and so forth. That's what you have in the participants table. Then you have the, what's it called? The courses or language table. So you have HTML, Python, CSS as several rows, right? And now you have the property table. You have participant course table. Are you hearing me? That's a third table now, where you have, say, Temitayo HTML. Temitayo also knows Python. Temitayo also knows CSS and so forth. And each other person too knows more than 2 languages. So that's another record. That is what is similar to this one here, similar to the person homework table. So if you're going to make an associative table from that, what you are going to have to do is bring the person ID, the course or language ID from the language table where you just had HTML, Python, CSS, and the rest. You take the person ID, you take the course ID, and you put them together in one separate table, such that the person ID and the homework ID come together to be your unique identifier in the associative table. So if there is a third column in that table, you want to know the proficiency of the person, then you're going to have Temitayo Python experts, Temitayo CSS beginner, Temitayo HTML advanced, and so forth. What this associative table is going to help you achieve is the unique property of one of the unique properties of databases, which is that each row should be linked to a separate record. Do you understand? So that way, in that associative table, what it is going to define for you is this person's level of proficiency in this particular language. So it doesn't matter whether the person ID appears 2 million times or the language ID appears 3 million times. The person ID and the language ID together are going to form your primary key in an associative table. And that is what I meant by a composite key. A composite key contains multiple primary keys in itself. So all these questions these answers that I'm giving have been provided as questions. So what is the primary key of this table? The primary key is not person ID, neither is the primary key homework ID. Rather, the primary key is the person and homework ID together, and it forms what is called a composite key. Do you understand? It's called a composite key because check it out. You realize that 5-1 as one primary key will only ever occur once in this table. Same as 5-2, same as 6-1, same as 6-2. Unlike what you have in, okay, this one is not big enough, but basically you're going to have repetitions in different places. Do you understand? So that's the beauty of associative tables. You have more than one primary key coming together. So, but what are the foreign keys in this associative table? The foreign keys are definitely the person ID and the homework ID because they refer to primary keys in separate tables. Do you understand? Now, if you wanted to create an index on this table, what indexes would you want to create? You would want to create an index on the person ID because it is a primary key, it needs to be associated with an index. You also want to I'm going to get back to you. You also want to create an index on your homework ID, right? So that you can identify which homework ID 1 is referring to. So anywhere you have something that is a primary key somewhere, you can create an index on that as well. Do you understand? So yeah, is it in this associative table that we have more than one index? Very possible. Very possible. But if you're going to make reference to this associative table in another table, then you can create an index for the combined primary keys of this associative table. Does that make sense still? Temitayo, does that answer your question? You're very welcome. Yetunde, do you have something to say? Seems like you are muted. Or can I push forward? Okay, thank you. So, many-to-many relationships. So now, why did we have to go through what we've just said with associative tables? It is because in your many-to-many relationships, it almost doesn't always make sense to explain it as the point of many people having many homeworks or many instances of this entity correlating or mapping to many instances of the other one. Rather, it is kind of like a transition between a one-to-many, many-to-one relationship between both entities.
Have they carried an phone? Yes, my transport already carried out.
Hi, could you please help mute? I don't have the host on.
Yeah, I was just looking for the person.
You look at
That BK2.
I found the person. I
Okay.
muted him.
Thank you.
All right, cool. Thanks. So, like I was saying, in the ideal scenario, you don't just have many to many per se. Rather, what you have is a transition. It's kind of like in a spectrum. You go from one to many of something before you then join that many of that thing to one. So it's a transition between a one to many and a many to one. That is what your many to many really is. So think of it like this. One person is going to appear many times in the person homework table because the person has done homework 1, he has done homework 2, he has done homework 3. So that one person appears multiple times in the person homework table. And that homework, this homework is also going to have multiple appearances in the person homework because homework 1 was done by person 5, person 6, person 20, person 3 million. Do you understand? So that is in the real sense, in the practical sense, how you really represent many-to-many relationships. So typically, if you're a database administrator or say a backend developer, and you have a case of many-to-many relationships, what you find out that you end up doing is you create one entity for one table for one of the relations, another table for one of the relations, and then you create a middle table where you take one person, one item from one entity, one item from the other entity, and you give us what is unique, what you're actually talking about as a third or multiple other columns. But basically, you're using the primary key from one relation and the primary key from the other relation as your joint primary key in that middle table. Do you understand? Of course, the person homework table is associative in this case. It is an associative table. That is why we had to cover it first here. As you can see, person homework, it's an associative table. Mustafa used an example. I just want to give another example so that it becomes clearer. He used an example of footballers and clubs. So we've seen footballers play in multiple clubs, and we also know that clubs at least have 11 players in them. Do you understand? So you can have one entity as footballers, another entity as clubs. Then you have footballers, clubs as your associative table, telling us that Cristiano Ronaldo as a footballer, Manchester United as club 1, he played between 2003 and 2009. Then go to the next row, Cristiano Ronaldo, Real Madrid, 2009 to 2018. Lionel Messi, Barcelona, 2004 to 2021. Lionel Messi, Paris Saint-Germain, 2021 to present. Can you see how footballers clubs becomes your associative table in that case, where you still have your footballers as one table and clubs as another table? Does this make it any clearer? Do we understand that analogy very well?
Yes.
All right, thank you very much. Exactly, know your footballers. I just geeked out on football there, but it's fine. Yeah. So we have talked a lot we've spoken a lot in very theoretical terms. So now let's bring it home. How do you apply these things in data science code? So very, very usual suspects. Everyone should be familiar and very comfortable with this guy, pandas. And this one would be more familiar to those with a stronger software engineering background, SQLite. It is simply a lighter version of your typical SQL. So what is pandas? It's a data frame library in Python meant for manipulating rows and columns, as opposed to matrices that have no labels with rows and columns. So now take note, pandas is not a relational database system. It is not a database system in itself, rather it is a tool that you use to replicate some form of functionality of relational databases. So let's not get it confused. Also, this course is not for covering pandas, but we're going to show some examples to let you see how pandas can be used, right? Okay. Sweet. I never knew that was what it meant, panel data. But yeah, that makes sense. That makes sense. Thanks, Pawalola. So to create a data frame. Now, what is a data frame? A data frame is simply a relational table. It's simply tabular data. Let's put it that way. You have your rows, you have your columns. You have your rows, you have your different columns, and you have an index for that, for each record. You have your index as well. So in this case, this is syntax for creating a data frame using pandas. This is a syntax for this is one of the syntaxes for creating a data frame in pandas. So you typically import your pandas and you run this code. So take note, this syntax takes it takes a list, right? It takes a list of each row, then you specify your column headers as another list of strings, right? So it takes the first parameter as your list of tuples. Remember that we said your relational data is typically represented as tuples or records. It's typically called tuples or records. So it's taking different tuples that would stand for the rows in your data. And it's also taking a parameter as the column names in your data. So this is very simple and straightforward. So if you run this, you get this. You get your column ID, which is the first column here, your last name and your first name. And it typically creates an index for you, pandas. For every data frame you create, it is going to create an index for you. And given our computer notations, we know that indices in our system usually start from 0. So you have 0, 1, 2, 3, 4, 5 for your 6 rows that you have created here. That is clear, I suppose. Okay.
I think you have some questions from previous aspects.
Oh, sorry. So Adedayo says, in the last explanation, the person homework should serve as both primary key and foreign key in different senses. Is this correct? So according to what we have covered, person homework in itself is a table. It is an associative table, right? So a table cannot stand as a key. But if I get you right, if I get what you're trying to Okay, Olayinka, please hold on. If I get what you're trying to ask, Adedayo, the primary keys in a table can serve as a foreign key in another table. That is in a different sense. That is correct. But in the person homework, your person ID and homework ID, they are not serving as separate primary keys. They are serving together as the primary key in this table. That is what it means. So the primary key is not person ID. It is not homework ID. The primary key is open bracket person ID, comma, a homework ID. You close it. That is what is the primary key in the person homework. But yes, these two that are the primary keys in this table can then serve as a foreign key in another table as long as this table is referenced. I hope that that answers your question, Adedayo. All right, cool. Olayinka, what is the last slide that you're referring to? Is it this one or this? It would be good if you unmuted, so just say yes or no. The data frame. Okay, do you have a question about it?
Maybe just general go over it again, if that's okay.
Okay, so what I was just explaining here is the syntax for creating a data frame, a pandas data frame in Python. It takes two parameters, a list. You can see this square bracket that ends here, right? So that's the first parameter. And what is contained in that list is tuples. Now, anything you have within brackets is a tuple. So it takes the tuple where each element is each item in a separate column. So they are comma separated. Each item in the tuple is what is the field it represents. So this represents field 1, field 2, field 3. And now the second parameter that this function is going to take, or this constructor is going to take, is the column IDs, the names of the column rather, and it takes it as a separate parameter, which is a list, ID, last name, and first name. So what that is telling you is this first column is for 1, 2, 3, 4, 5, 6. Last name is for Coulter, Williams, Dan, Jane, Gates, and Musk. And the first name is Zico, Josh, Chen, Mayank, and Bill. So after you run this and you print out DF, which is the data frame, this is what you are going to get. This is how pandas represents a data frame, which is simply, oh, that's a very, very good question. Sorry, I had to cough. Yes. So, well, not Python particularly. The point is you need to have some programming knowledge to be able to do data science. And depending on whatever platform or whatever language you're using for your data science, so we're using Python here. There's also R, there's Scala, and there's the archaic people who still do Python data science using Java or the rest of them. Basically, the idea is you need to have some programming knowledge. So if you're going to use Python, you need to have a good knowledge of Python to be able to do data science. There's no running away from it, to be fair. There's no running away from it. If you're going to use R, you need to understand R. You need to have a good knowledge of R as well. There's no running from it. If you remember in the first class, when you were doing the meaning of data science, the definition, you've been told that it's a multidisciplinary field. You need your domain knowledge, you need your statistics knowledge, and you also need some programming knowledge as well. So you can't totally run away from it. I hope that answers your question. Yeah, but don't get overwhelmed. I'm saying wow. You take it one day at a time. It's one day at a time, no rush. One day at a time, steady, and you would get there. And Python is also a beautiful language where you learn as you do. So you can literally start Python today and start doing some things. You won't do everything, but you can start as long as you pace yourself and you manage your expectations very well, you'll be fine. Trust me. Exactly, Mobia. So now they say operations in pandas are typically not in place. They return a new modified data frame every time rather than modifying the existing one. So you have to do two things to make a change to your data frame. You either use the in place flag or you assign that new action to the old one in itself. After this slide, I'm going to go into the code so that we don't get lost. So if you select a single row in pandas, it is going to return a series object, which is a 1D data frame, but doesn't have multiple columns. And it is also not well formatted. All right. Enough of all this English, and let's get into something interesting. Okay, so this is our syntax for creating a pandas data frame. This is not large enough. I know before you guys say anything. Can you all see my screen now? Can you see the code very well now?
Yes.
Can you increase it a little bit more, please?
Better?
Yeah, better.
Okay, sweet. So this is simply the same thing that you've seen on the other page, and it's going to create your data frame for you. So let's rerun it. As you can see, it's taken the data frame or the parameters that we've given it and created a new data frame for us. This unnamed column, or what seems like a column, is the index of this data frame. And these are the 3 columns that the data frame contains. All right. So now what you can then do is set your index, because like we said, the index is going to be used for searching. So if you wanted to change the index of this data frame to your ID, which if you had in a normal database system, an SQL database, that is what it's going to look like. You use this command set index, right? Set index ID, and this is what it's going to give you. So now this is what it's going to give you. But then after you do this and you try to print your data frame again. So let's run this. You expect that this is what your data frame is now, right? But that's not the case because your data frame is still as it was the other time. Do you get me? So this is it. Your data frame is still as it was. So what that means is it doesn't do it in place. No, this is not Colab. This is VS Code. So what this means is when I say it doesn't do it in place, what it means is it only gives you a view representation of what that command would be. So if you really want it to happen, as you have said, you need to set an in place parameter, right? So that's what it is telling you here. So you do the same thing and you say in place is equal to true. And then your data frame becomes like this. An unclean way to do the same thing would be to say df is equal to so this is very clean. This is what is advised. This is another way to do it, but it's not the cleanest way, because what that means is you're just creating a different object and it's not exactly changing. It's almost like you're creating a clone. Somehow, somewhere, there's something lurking in memory. So it's not very clean. But when you use the in place parameter, what that means is it is telling you that this data frame sets the index to this and actually do it on the same data frame. So you're doing it in place. That's what they mean. So this is what your data frame now looks like. So
could you please
someone,
yeah. Can you hear me?
yeah, I can hear you.
Okay, could you please go back to the code? I was just going to say that, can you highlight on the code? Like maybe like do a comma, try to want to write a new thing. I wanted to show
The
the audience,
parameter.
yeah, just for them to see that you can already see all the parameters that this set index take in. You can read and you can try to familiarize yourself with it. It's a good way if you're coding. If you don't know what comes in, a lot of this packages come with well-defined, readmes and everything, which you can use to understand what the function takes in and help you, learn more. I just wanted to mention that.
Yep. Yeah, also
So you can
it's
see in
literally
place.
like a snapshot of the documentation.
Yeah.
So if you don't want to go to python.org to
So
get all
look,
these plenty things.
look at the in place there. You can see in place. It says in place. It's a Boolean. It's supposed to take true or false. It's default
Yeah,
to false, and we just turned it to true now. If it is true, it modifies the data frame in place. It does
and
not
it does
create a
not
new
create a
object.
new object, which is what df is equal to the other one might have done in terms of memory and the rest. So yes, thanks again for that, Tedro. So guys, and also if you just want to see documentation when you're writing, depending on the machine that you use, actually it's the same. Control space is for IntelliSense, right? Depending on the IDE that you use, you can see the different functions that are available, different tools that you can use, and when you are inside the function call, use the same keyboard keys, control space, to view other parameters and things that you can use. You understand? Okay. So now something was mentioned here called a series. Now a series is simply each of these columns returned. So what it means is it's going to have an index, quite all right, but it is not formatted. I mean, pandas did not see the reason to go through all that stress. So how do you call a series? Let's quickly write something here. So you call the series. A series is simply a pandas data frame column. So let's say, what are they called here? First name. So you can see it has returned the first name column as the name. It's an object data type. I mean, that's strings and all. But you can see that it is not as formatted as the proper table. So what you're usually advised to do if you want it to appear as a data frame is you are trying to get, you make it appear like you're trying to get a list of columns, and then it is going to appear well formatted. Do you understand? So these are just simple hacks, but then you understand what a series is now and what a data frame is. So another one, let's go back to the class. So I will follow one by one. So now some common pandas commands, read CSV. We familiarized ourselves with this last week. Head, the head function, then you have the location and you have the index location. So loc is LOC, iloc is index location. Let's see what comes next. Okay, before we go to SQLites, let's quickly play with some of these commands, right? So we looked at head. So what head is going to do for you, data frame.head, is it's going to return the first 5 rows in the data frame. What's this now? Didn't open the terminal. Did you get? So it's going to return the first 5 elements in your data frame. But what it also means is the way it is implemented, 5 is the default, right? But you can specify a number. So you can say head 100, head 1 million, head 1,000, depending on how many rows are contained in data frame. So what the real definition of head should be is, so I didn't change anything. If you have the latest update of VS Code, you can write notebooks within VS Code. That's all. And the Jupyter server, given that it's VS Code that provisions the new notebook interface, it automatically knows that it's using an adaptation of the Jupyter server. All you have to do is specify the Python kernel that you're going to use in the IDE, and you're good to go. You literally don't have to do anything. Get the latest VS Code updates. You're going to see it in the release notes. Create a file, save it as IPYNB, which is Jupyter Notebook format, and it automatically knows that it's using the Jupyter server. Okay, so like I was saying, what the head can be defined as really is to give you the first n rows of your data frame, right? So, but by default, if you don't specify n, which should be a number, it's going to give you the first 5. And as with all things in this world, na double. So as you have the head, it's the same way you have the tail, right? So what the tail is also going to give you is the last n rows contained in the data frame. And by default, if you don't specify an n, it is going to give you the last 5. So let's see what df tail is going to give us. You can see it's giving us the last 5, starting from the end, 6, 5, 4, 3, 2. Doesn't give us the first row. Do you understand? So that is one. Now, another one is the loc. Loc simply means location. Let's see what it's telling us. It's telling you it's primarily label based. Can you change the 5? Yeah. That was what I was saying. If you wanted to give you the first 10 or the last 10, it's going to find all of them for you. Do you understand? So I've changed it. I've overridden the default, which is 5. And you can see it's giving me 6 because they're not up to 10, but it's going to give me everything up until 10. So we're just reading the documentation of .loc. So this is, like Teju mentioned earlier, this is one of the best ways of understanding what you can do with Pandas data frame objects. They have many callable functions and methods and attributes that you can always call. So it is simply going to get you a group of rows and columns. That's simply what it's going to do. What does it take? It takes the first row and the column that you want it to return for you. So location takes the position, right? And the column. Does it make sense? Can someone tell me why it is C and not Coulter? Why has this line returned G and not Coulter?
I think that's because the index is 1.
Thank you very much. Yeah, that's a simple answer. Indexing. Thank you. So it is using the index. So don't get it confused when it is using the ID. And that is why if you feel it's going to get confusing, you use the set index command, right? You use the set index command to return your data frame as with the ID as the index, and then you can go ahead and use it like that. Does it make sense? I believe that is.
Yes,
So
it makes
now,
sense.
yeah, thank you very much. So now there's this character, this colon, when you're dealing with lists and apparently, yeah, actually with lists, it's called a wildcard, the column. And what it does is, depending on the position you have put it in your list or wherever, it is going to, yeah, we're getting there, Akintayo. We're getting that. It is going to return everything contained in that position. So now when you have a data frame, it's a two-dimensional object, right? You have rows and columns, two-dimensional. So typically, whenever you want to locate something in a 2D item, same as your, whether it's a NumPy or pandas objects, you need to specify the X and Y, or the M and N rather, rows and columns. So wherever you have this column wildcard in any of the positions, so in this case, row before column, if you say colon, you're telling it to return all the rows for you. Return all the rows containing which column? This guy last name. And that's why it's giving us everybody's, this is why it is returning everybody to us. It's returning everybody's last name. If we wanted this location to return everything everywhere, so give us all rows and all columns. Ta-da! Do you get it? So that's what this wildcard simply represents. But we're not looking at Python locations here. So this is still look. Now iLook should be down here somewhere. So if you wanted to check iLook, it's going to give you dates. First and foremost, let's see what DF is looking like these days. Okay, right? So you
I'm
can
not
see,
sure we are seeing what you're talking about.
this is where I am now. Hello, can you see my cursor now? I'm here.
Yes.
No.
Okay.
I can see it though, but maybe everyone cannot.
Can you see it now?
Okay.
Oh,
It seems we
okay.
have multiple people who can see.
Yes.
Okay, so it's basically so now if you wanted to use iLook, then with iLook you have the power to specify an index positioning for your column. Yeah, so I don't think I ran that. I didn't run it, Michael. So let's go back there so that we see, say it's not like, I actually didn't run this after writing the syntax. So when you do that, then df ideally should become what? ID should become your index. Does that make sense, Michael? Yeah, I think you should be fine with that. So now notice that with lock, all you had to do was, or what you had to do with location was specify the row index. You could use an index identifier for the row, but for the column, you have to specify it. You have to specify the name of the column as a string or using the wildcard character. right, to specify all of them. But with iloc, with index location, you can specify number characters, like index-based characters for the row and index for the column. Does that make sense? That's the difference between both of them. So if you said iloc, that's position 4. Now, if ID is our index, then 4 should be Mani. The last name that should be returned is Mani, right? Oh, still counting as 0, 1, 2, 3, 4. Okay. So it's still counting 0, 1, 2, 3, 4, apparently. So it's using the index positioning, using the pandas default. Okay, yeah, thank you, Akintayo. So apparently it's actually going to start from 0 using our typical, look at it, it is using the 0 index counters for both the rows and columns. So it doesn't matter whether it's the ID is something else, it's still going to use the 0 index counter for both of them. So if you say position 4, you're counting 0, 1, 2, 3, 4, and 0, 1, 0, 1, 2, 0, 1, 2. So 1 should be the last name. Yes, so thank you. So now we can get into SQLite. Yes, yes. I mean, there's so much, like there are so many functions and properties that we can't possibly exhaust all of them, but depending on your use, depending on your scenario, you can always find many of these functions that you need. So now, SQLite. SQLite is an actual RDBMS system, relational database management system. It is a serverless model. So it is not like your MS SQL, MySQL, or the rest of them that you need to install a server and connect to. With SQLite, it's simply a file on your local machine that you can always access as soon as you need it. So it allows for simultaneous connections from many applications to the same database file, but it is not as big on concurrency as client-server systems. Anyone who has used SQLite would know that this is an issue. Your system might fail if you try to try to access a record or something multiple times, like from multiple places at the same time. So all operations will typically use your SQL, structured query language, and you cannot enforce foreign keys in SQLite, but we're not getting into that today. So before I continue, are we all familiar with SQL? Hey, I like Oluwafemi. Didn't even miss his words at all.
Yes, to some
Good
extent.
here.
No.
Nope. Okay. To an extent, somehow. These are interesting answers. Basic. Yeah. Okay. So for this, and thankfully, for most of what we'll be doing as data scientists, hear me out. For this class scenario and for what we'll be doing as data scientists going forward, that is in our career or wherever we find ourselves, we wouldn't need to know beyond the select statements and the join commands. Yeah, okay, so those listing MySQL and PostgreSQL, yeah, you're familiar with SQL, those are SQL servers, right? But yeah, there's Transact SQL, which is See, basically, the syntaxes for MySQL and PostgreSQL and MS SQL, they differ in tiny bits, but yeah, that makes sense. Yes, TSQL, Transact SQL. So for the purposes of what we're doing and going forward, hopefully, unless they mix your job with that of a data engineer, you wouldn't need beyond the select statements and your where and join clauses in SQL. Okay, so to create a database in SQLite, first you import the SQLite library. Oh, yeah, I already have SQLite installed on my machine. So it's going to run one time, but if you don't have it installed, you know the typical way, you use your pip to install SQLite 3. Then the first thing you do is you establish a connection, right? You establish a connection, create a connection object, SQLite.connect, and create a database while you're at it. You create a database, then your cursor is going to be whatever. And you can start using the connection object to run commands. So you use con.close to close your connection. Then you use cursor.execute to execute commands, basically. Let's look at this question. Femi. Okay. So you typically use, apparently, yeah. Everything is all together these days. So you typically use the execute command to run commands and yeah, basically to run the command. So if you don't call commit, now there's this thing in databases. For those who have worked with databases before, you need to commit your changes. It's, you know, the way in Git, anything you do, you commit your change and push. So the commit, you need to commit everything that you've done on that connection. You commit it so that your database is changed and it is in place. Otherwise, you're just going to be seeing views of what you have done. Then if you don't call the commit, there's also a command known as rollback. Rollback is like revert. It's like revert. So you use it to roll back to wherever it was before that commit. Very, very important, especially for those that will be working with databases directly. Very important. I'm seeing questions here. SQL is a programming language on its own. Yes, that is true. SQLite is part of a Python library. I don't quite think so. It's a library that you install and you start using within Python. So like Teju said, it's a Python wrapper. Are the commands the same for SQLite and others? SQLite, you will be using SQL queries, like SQL commands. That's what SQLite uses. It uses normal SQL commands. I hope that answers these questions. Okay, let's get into the code. I think we're almost at the end. Yeah, so let's quickly look at the SQLite code and we can move from there. So import SQLite. So there are different providers for, okay, we won't go too far, but just quickly look at this, show you that it works. Does it have its own ID, so to speak? Yes, there are different providers. I would always recommend dbeaver for SQLite. I've closed it, but no worries, I'll show you. Just to run the command, you can see it creates the database. It's going to create the database for us. Yeah, database.db. We've just asked it to create it for us. Just wanted to show you that. Then you use the cursor.execute to create different tables, right? Different empty tables. Oh, table person already exists. Okay, I didn't delete the database before actually. So it already exists. This is the error that you're going to get if it already exists, right? So let's insert these values into the database like we have. So you're simply executing the command using the cursor object. And so are you seeing these errors that we're talking about? This is one of the things I said about concurrency. Yeah, definitely it's in the notebook. Hello. It's one of the things about concurrency. Now I'm trying to access the database. I'm trying to write to a database from multiple places, apparently. So that's why it is locked. So it's one of the beauties of databases. So you can't always, you can manipulate it from multiple places. But by the way, let's run this. We want to see everything. For row in execute, select all from person, print row. That's what it gives us. Nobody is there. Okay. Just run all of this into trash and we start again. Can we see? This guy should work now. So that's fine. Now we are going to have items in our database. I want to believe this is very clear. It's very clear, simple and straightforward. You can always make reference to the notebook again. I'm going to share it after the class. So the last thing that we're going to cover today is joins. And I think we've even spent too much time on the others because joins are very, very important. So what are join? Join operations are simply ways that we merge different tables in relational systems or in pandas as well. And we have four main types of joins that we have. We have the inner join, we have the left join, we have the right join, and we have the outer join. Typically, whenever we hear about join, let's relate it to sets, intersection and union, right? So the easiest explanation for inner join is intersection. In sets, the intersection of two sets is what they have in common. Yeah. What the definition of intersection in sets is what two sets have in common. In other words, it is only what they have in common that you return. That's what you have as inner join. For left join, what you are doing is you have two different tables. You keep everything in the left table, right? You keep everything in the left table, return what they have in common, and whatever is not in common contained in the right table, you dismiss it. So whether the left table has anything in the right table, it doesn't matter. You return everything in the left table as it is, and you fill it up with blanks for what is missing in the right table. Let's go from page to page. So you want to join person and grades, right? You have person ID, homework grade 1, homework grade 2. If you wanted to join this table, these tables, you need to specify the columns that you're going to do the join on, because that is what they can have in common, correct? So you join the two tables where we only return rows with two joined columns that contain the same values. In other words, so you have gates. So we're joining person and grades based on person ID, right? So the ID, you're looking for 1, 2, 3, 4. You don't have them, but you have 5 and 6, and you have 5 and 6 here as well. So to do an inner join, you're only going to return where these two tables are the same. So person ID and ID. So you're only going to return Gates and Musk, and you're going to join both of them. So Gates William 380, Musk Elon 380. Let's see. Exactly. Does that make sense? This is an inner join, and it is also known as an intersection. if you're looking at sets, it is an intersection. So this is the syntax for running inner join in Pandas or SQLite. I'm going to share the notebook after, so you can always try it, but please also engage the GitHub discussions as well as Slack to ask your questions, please. But typically, Pandas has a function, read SQL query, that takes your SQL command as well as a connection to the database, right? So when you run this together, it generates the results and saves it in an object. So, but to actually carry out the join, in Pandas, what you do is you take the data frame and you use the merge command. So the merge, what does merge take? You use merge on one data frame object, and the first parameter it takes is the other data frame that you're trying to merge on. Then it takes another parameter, how. How is one of inner, left, right, or outer joins, right? So you specify how you want to do the merge, how you want to do the join. Then you say left on, right on. So now there's also on. So there are some other parameters on, you have left on, you have right on. So now if in the two tables, the column names are the same, then you just say on equals that column name, right? But if the column in the left table is known by something and in the right table it is called something else, then you have to specify left on this one, on this column, and right on the other column. So take a look again. In the first column, you're doing left on ID, but in the second column, it is on person ID. And that is why the syntax is saying right on person ID. I hope that makes sense. So that's for Pandas. If you are going to do it in SQLite, that is SQL command, what you simply say is select all. It usually goes in the syntax, select all from a particular table where this ID from this table is equal to the column in another table. So you're selecting from both tables where the person ID is equal to the grades.person ID. That's the syntax in SQL. It's simple, could be confusing too, but please go ahead and ask questions on the GitHub discussions. So now for the left join, like I explained, it's going to keep everything that you have in your left table, but introduce nulls into the right table where there is no match. So now when we did the inner join, we realized that there are only matches for person IDs 5 and 6, correct? For person IDs 5 and 6. But because we are trying to do a left join now, we're going to keep everything in our left table. But the right table doesn't match any of these guys, so it is going to represent them with nulls because there is no match there. And you can't return an L-shaped table. No, you're going to have to fill it up so that it maintains the shape, and you only do that using the null character. That is what a left join is. And can someone just tell me that if left join behaves like this, how do you expect the right join to behave? Anyone?
Then I suppose it keeps the identity on the right rather, and then it fills the empty one on the left with null.
Exactly. I like the term Michael used, mirrored L. Just shifts it, like exactly, it's the opposite. So for your right join, it's going to do, okay, so for your left join, if you're going to do it in Pandas, your OW is going to be left, same thing applies. But in SQL, you're not just using the where clause, you're going to have to specify the left join. So if you're going to do the right join as well, you're going to do the right join. So this is how you do that. And for your right join, the reverse, you keep everything in the right, correct? You keep everything on the right, and you null out the places that are missing in the left table. Very simple. Very simple. But now for the outer join, what does that mean? The outer join is your full union. In sets, what does union mean? Union is everything in both sets without repetition, right? Everything in both sets, but without repetition. So that's what your outer join is. It's going to return everything from your left and everything from your right table, and it's going to put the nulls where they are meant to be, that is where they don't match. So it's simply doing a left join and a right join and putting the tables together. So as you can see, thank you, Adara. Yeah, thank you. No, 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 no. It's not the universal set. You know why? Because the universal set is everything that is possible. In this case, the two tables that we have, they might appear like a universal set because that's what you know. But given where they come from, there might be some other tables with some other record, with some other items that might be contained in the universal set. So it's just a union of these two. Yes, Akorede, you do need the right and left, but it depends on your use case. So now let's go away from geeking databases and come back to why we're actually looking at these concepts in data science. Depending on what you are doing, depending on your use case, you probably want to maintain information in one table and only get what is missing or what you have from the other table, and so forth. So think of it like this. Look at the result of your left join. You can see that it is a 6-row result, right? It means that you probably have more observations maintained. And look at the result of your right join. Just 3 results were returned. Just 3 rows, 3 observations were returned. And now look at the result of your outer. You have 7 rows. So you can see that depending on what you want to do, you choose the kind of join that you want. Sometimes you only want information from the left table and what is common on the right table, and that's why you do your left join. Sometimes you only want what is in the right table and so forth. Do you understand? So there are different uses. It has to be your use case. It has to be your use case to know that, okay, this is what I need to use. I hope that makes sense. So yeah, either join produces null values, especially when there is no match. That's when there is no match between both tables. However, if you have all of them fully matched, then you're going to have a very well-defined table without null values. So yeah, no repetition, very important. That's the beauty of sets anyways. And actually, that's the end of the class. So let me quickly open the notebook and see if we can quickly run the commands so that we see what we're talking about. How does joins relate to the concept of associative tables? That is very, 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 very important. Very simple. Because you know that the associative table is what do you call it now? The associative table is a combination of 2 tables, right? You're taking a field from one table and taking the field from another table. So you probably do an outer join, right? First and foremost, just so that you cover the full extent of possible records that you have. You do an outer join on both tables so that it returns all the unique person IDs, as well as homework IDs. I'm using the person homework as an example. So when it does that, right, then you can take the last column from the homework table. I don't know if you get what I'm saying. So you do a join on person, you do a join of the person table and homework table, you do the join on person ID. So left on ID, right on person ID, and you return all the homework results. And that's how you get the person homework table. I don't know if that answers your question, Hugo. Thanks. Yes, that's a good point, Elo. Joins are used to combine tables. Associative tables show the relationship between two tables, but you need to create that associative table as well. So if you are going to create that associative table, you're actually joining both tables also. You get? Yeah, but that's when you already have the tables existing. In a real sense, of say you're building a system and you want to incorporate it from the start, then you're going to have to collect those records separately. What do I mean? Say it's a transaction system, right? It's a transaction system. Let's use an example of a loan case, right? Different people would take different loans at different times, right? And each person or these people are going to also repay these loans at different times. So some loans could be 6 months, some loans could be 12 months, but you make payments every month. In other words, me, if I've taken a loan that takes 12 months, ideally I'm supposed to make 12 payments to repay my loan, correct? So at this point, whenever you're collecting that transaction information, you are going to have to put my name, you're going to have to enter some records in the user table, that's me. You're going to have to put some records in the loan table, that is the amount of the loan that I took. And you also have to put some records in the transaction table, which is going to be my associative table in this case, the relationship between me and the loan that I took. So you're going to have to put in multiple records in that transaction table. So that's a practical sense from a user perspective, but you're already in the back end, you have all your data. You're going to have to join the tables manually. So that's why you're using the joins to create the associative tables. I hope there is no confusion or there isn't too much confusion. All right, thanks a lot. So yeah, I'm pushing the notebook to GitHub right after this. And please, I didn't see so much engagement in the last class, in the last discussion tables. But yes, please, I would like to get a lot more discussion because trust me, this is very, very fundamental, very, very fundamental. And for me, you say there's confusion. Let's see if we can help you. You can unmute yourself and ask a question for me. Okay, I expect you mean the transaction and loan explanation. So what I am saying is in a typical loan system, different people would take loans at different times, and each loan has a repayment term, right? So it makes sense to keep a record of each user, that is each customer of that organization that is giving out the loans. So you have a separate record for the customers, and then you also have a separate record for the loans that have been taken, right? So in such portfolio table, you're going to have, let's say me, Tayo, I took 2 million naira from these people, and I'm supposed to pay back in 6 months. This same Tayo, I took 5 million naira, and I'm supposed to pay back in 12 months and so forth. What I'm trying to let you know is Tayo as a person could take multiple loans. He could have multiple appearances, right? It's the same way if, say, you Fumi now, could also take multiple loans, one or more loans from the same organization. But where the idea of the associative table is going to come into play now is the transactions for your repayment. Because given that I'm supposed to pay back in 6 months, I'm expected to make 6 payments, right? And if you took a loan that was for 10 months, you're supposed to make 10 payments. The best way to save that kind of record is to have a separate transactions table that has your person ID as one ID, your loan ID as another ID. Together, they become your primary key. And then the amount you paid is another record. The date you made that payment is another record. That way, there's no way they are going to look for your payment information, that they are not going to get information that relates to only you. Do you understand? So I was making that example as that's a very, very practical use case for associative tables and so forth. Okay, you're very welcome. I have gone over my time by about 3 minutes. I think you're supposed to be on break now, and the practical session would start at 12:30. Am I correct, Pedro?
Yes, thank you so much for the class today, Tayo. It's very informative. We started a little late. Apologies for the technical difficulties, but all is good now. We should start the practical session by 12:30, and it means that we would have to stay a little longer, 30 minutes. So I will stop I will close this Zoom and try to start it again because I needed to have the fix that I made for the previous one so that we can stream on YouTube directly. But yes, 2 things before you go, please. There is the attendance sheet. Please fill the attendance sheet, but also very, very important for us as organizers and instructors is the feedback form. A couple of us fill the feedback form. It's usually low turnout compared to the attendance sheet. I understand, but this feedback form is not like one of those feedback forms that take all of your time. Literally, it takes like 1 minute or so. We are not even asking you for so much, just whatever you feel applies to you, just let us know so that we can learn from it, understand where the struggles are. We are not using it to judge or anything, it's just for us to understand how to tailor the materials to the audience. So please endeavor to do that as well. Yes, is Femi on the call? Do you have announcement? I'll stop recording now and I'll upload it on YouTube.